right, so here we are back at it again, and we're going to write the series in summation notation. So here's kind of your steps of what you need to do. You're going to write your rule. So we're going to continue practicing writing those rules that are not arithmetic, not geometric. We're just going to take our time. We're going to kind of think about those outside the box rules. Then we're going to determine the number of terms. So once you figure out your rule, figuring out what the number of terms is isn't difficult at all. And then you pop that into that sigma notation. Remember sigma notation? That's that summation notation, that fancy E. So as we look here at this first pattern of numbers, 1, 8, 27, 64, go ahead and take a minute, pause the video, try to see if you can come up with what the pattern is. All right, so now you're back. You've figured out, hopefully, that the pattern is that we're dealing with perfect cubes. Okay, so if we kind of keep that same model, you know, our first term is 1, our second term is 8, our third term is 27. So how are we changing this n, this term number, into that 1? How are we changing 2 into 8? How are we changing 3 into 27? Well, we're taking that n, we're taking that term number, and we're cubing it. So right here, this is my rule. Now, really, if we write the rule, we'll need the a sub n, but when we put it into the sigma notation, we just have the rule. So I'm going to go ahead and set up my sigma notation. The rule goes right here, so maybe you're writing yourself some notes here. And then this usually just starts at n equals 1. Now, whatever letter you use in your rule, you have to use down here. So if you use an x there, you're going to use an x there. If you use an I there, you're going to use an I there. We're going to use n just because that's what we're used to. And then you've got to figure out this top number. This top number up here is the number of terms in your series. So that's really the term number of the last term. That's what that is. So I've got to figure out, well, what is this? This right here, if this is my rule, I can just figure out what that n is by taking n to the third equals 729. So I can figure out what n is by using my rule and using that last term. So you can see, take the cube root of each of those, and you get that n equals 9. Remember what kind of number n has to be? It has to be a natural number, and that 9 is fitting just right. So I'm going to put that 9 on the top because that's the number of terms that are in my series, and then I'm putting n equals 1 down here on the bottom because I'm starting with that 1 cubed to get that first term of 1. So there, I've written it in summation notation. Let's try another one. So now as you look here, I have 6 times 36 times 216, and then dot, dot, dot. So because this is dot, 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 as we're thinking about that sigma notation, we need n equals 1, we need our rule, and then we need our ending number. Well, we don't have an ending number. So because we don't have an ending number, that means that this is an infinite series. That's okay. We've seen those before. So as you kind of figure out what the pattern is, take a minute, see if you can figure out what that is. Maybe you notice that, hey, we're just multiplying by 6 each time. So because we're multiplying by 6 each time, that's just a geometric sequence. So you could write your rule. So there's that formula, right? My first term is 6, my ratio is 6, my exponent's n minus 1. So this right here, that would be an appropriate rule. Some of you might have been like, well, you know what, that's not the rule that I thought of. I thought about this rule. I thought about the rule of just 6 to the power of n. 6 to the first power is 6. 6 to the second power is 36. 6 to the third power is 216. Honestly, guys, it's the exact same thing. If you were to simplify this, if you were to think about this being 6 times 6 to the n minus 1, this is really 6 to the first power. Remember, to simplify, you need the same base and the same exponent. We have the same base. So if we add those exponents together, you just end up with that 6 to the n anyway. So either one of those is fine. You can use this as your rule, or you can use that as your rule. Doesn't matter. When n equals 1, you're still plugging n equals 1 in. You're still going to get that 6 for your first term with either rule. So if we think about our rules, that's a funky sigma. We can have that where we start at 1 and we go to infinity. That would be a-okay. Or this would totally be fine as well. We have that geometric pattern still going to infinity. So 2 right answers there. It's pretty neat. All right, let's make it a little bit more challenging here. So sometimes when you're dealing with fractions, sometimes you have to think about the numerator separate from the denominator. Can you find a pattern in the numerator, can you find a pattern in the denominator? Sometimes there's not one thing that's taking us from 3/4 to 5/8, and then the same thing taking us from 5/8 to 7/16. So sometimes you can split fractions into a top rule and a bottom rule. So sometimes that happens, but sometimes that doesn't happen, okay? So you've got to kind of just go case by case. You're trying to see, you're spending some time, you're trying to see, I can't find a pattern. I can't find something that takes me from 3/4 to 5/8 and that same thing that takes me from 5/8 to 7/16. So you can start breaking it up and say, okay, well, look on the top, 3, 5, 7. Okay, so on the top, you can see that we have an arithmetic rule. We're adding 2 each side. And then on the bottom, you can see that we have a geometric rule because we're multiplying by 2 each time. So as I think about writing an arithmetic rule for the top and a geometric rule for the bottom, you're just writing your arithmetic and geometric rules. You're just kind of squishing them together into a fraction. So if I want to deal with that arithmetic rule, I'm going to say a sub n equals that first term plus n minus 1 times that common difference of 2. Remember that we want to simplify that. Look a little fuzzy. That looks better. Okay, so we're going to simplify this. So 3 plus 2n minus 2 is going to be 1 plus 2n. So that's my rule for the top. That's that arithmetic rule for the top. Now the geometric rule, remember you're going to just go a sub n equals a1 times that ratio to the n minus 1 power. So there's that bottom rule. Arithmetic, geometric. So as I think about starting to set up my sigma, I'm always starting down here at n equals 1. My rule for the top is going to be that 1 plus 2n or 2n plus 1 either way. And then my rule for the bottom is going to be 4 times 2 to the n minus 1. So now the last thing you want to do is you want to figure out what this ending term is. So what this ending term is. You really have 2 choices. You set the top equal to the top, so I could solve 1 plus 2n equals 15. Or you set the bottom equal to the bottom. I could set 4 times 2 to the n minus 1 equals 256. You choose which one you want to solve. I hope it's obvious, okay? This one's going to require you to use logs. This one you're just going to subtract that 1 and divide by 2. So we get that n equals 7. So that n equals 7, that's going to be that ending term number that you pop up into the top. So there we go. All right, we got one more of these writing rules and putting them into a sigma. So again, we have a fraction. So as you're looking at the fractions, take a minute. Try to see if you can figure out what that pattern is. Pause the video. Try to really come up with what that is on your own. That's one of the hardest things, is just trying to figure out what that pattern is. So you're coming back now, and we're looking at the numerator separate from the denominator. Hopefully you're seeing that the numerator, those are your perfect squares. Okay, you can kind of see we have plus 3, plus 5, plus 7. So we're sticking with that double plus is going to be a perfect square situation. Now the bottom, I think we did that already today. At the very beginning, we found this pattern, 2, 5, 10, 17. So maybe you remember it, maybe you don't remember it, but all it is going to be those perfect squares plus 1 more. You can kind of compare also the numerators to the denominators. Each denominator is just 1 more than the numerator. So the bottom is going to be perfect squares plus 1. So as I think about my rule, okay, my rule for the top is perfect squares. So perfect squares is just going to be n squared. 1 squared, 2 squared, 3 squared, 4 squared. And then the bottom is going to be that perfect squared plus 1 more. And you might come up with other rules, okay? If you are coming up with other rules, no big deal. There's not necessarily just one right answer. Just make sure that whatever you're coming up with, that it works for all of them. So now we put that into the sigma, the summation notation. Remember, you're always starting here down at n equals 1, and then where are we ending? So like, what's our ending term? Because this is just dot, 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 because there's not some ending term like the last one, we're going to just say that we're going to infinity. That's what that means. All right. Last thing we're going to do is we're going to find the sum of a series. So we found the sum of arithmetic series. We found the sum of geometric series. Now we're going to find the sum of one of these other series. So you can see that we go from 3 to 7. So we are going to find the third term, the fourth term, the fifth term, the sixth term, and the seventh term. So we've expanded series before where I'm going to plug that 3 in. So then I do 3 squared minus 1, and then I'm going to get 8. So if I asked you just to expand the series, I would be doing this. So then I'm going to take 4 squared minus 1, and I'm going to get 15. And I'm going to plug in 5. 5 squared minus 1, and I'm going to get 24. And then I'm going to plug in 6, and I'm going to get 35. And then I'm going to plug in 7, and I'm going to get 48. So this right here, this is the expanded series. Now, there is no shortcut. We saw some shortcuts on how to find sums for arithmetic and geometric, but look at this pattern right here. This k squared minus 1 doesn't look arithmetic. It's not one of those linear functions, and it's also not exponential, so it's not that geometric pattern. So there's no shortcut for this. You have to just plug in all of them. So you're going to be so grateful that we just gave you from 3 to 7. Plug in 3, 4, 5, 6, 7. So then go ahead and pull out your calculators and then actually do the addition. So when you actually add them together, you're going to get that your sum is 130. All right, so last one here, I'm asking you to find the sum from 1 to 40. So we could do it like we just did the last one where we plugged in 1, then we plugged in 2, then we plugged in 3. But holy cow, do we want to plug in all of them up until 40? So as you look at this, you need to start remembering this is just an arithmetic sequence. Okay, this is arithmetic. We know that this is arithmetic because look, it's linear. It's got that y equals mx plus b format to it. So you have to be able to see if it's a linear or if it's a exponential, if it's geometric, then you know that an arithmetic sum, hopefully you can take out your green sheet and you can say, okay, my sum is n over 2 times a1 plus an. So all I need here is I need my first term, I need my last term, and I need that n. Remember how you find n, top minus bottom plus 1. So make sure you're in that habit, n equals 40. A1, we're going to find A1 by just plugging in 1 to your rule. This is my arithmetic rule. So 2 times 1 minus 1 is 1. And then we need our last term, so that 40th term. So 2 times 40 minus 1 is 79. All right. So now we're going to go ahead and plug this into our formula. So we get that our sum is 1,600. So yes, the sum of those 40 terms. Yes, we could have added together and found all those individual terms, but that would be very time consuming. So the point of this is just make sure that you're looking, make sure that you're checking, make sure that you're not forgetting the arithmetic and the geometric that we've worked so hard on. All right, guys, you're doing so great. Go ahead and check out the homework.